yet another really cool exercise about bases and maps. Remember, we have now iterated this multiple times, that a matrix is a map and a map is a matrix, a linear one, of course. And we would like to see what this very simple map does in a new basis. We assume, of course, that this is represented in the standard basis, and that is 1, 0, 0, 1. So how do we find the new map? The answer is simple. You have some elements in the standard basis which are represented as some constant times the old basis, which is the standard basis, just the identity matrix, you could say. This is I and this is J, just the normal directions as usual. This is how I can represent any space, any vector in R squared. But if I want to write this vector in the new basis, which is it will have a completely different set of coefficients. It will still be this vector x. It will be exactly the same vector, but we represent them in two completely different ways. This here we represent it with this basis. Here we represent it with the new basis. Okay, how do we discover the action of the map in the new basis? This is the action of the map in the old basis. Well, the idea is pretty simple. All we need to do is to look at the action of the map on the basis vectors. And whatever action will happen on the basis vectors, you could say this will be transferred to the vector when you attempt to write it in this new format. Because if you have a basis, you write every single vector in terms of this basis. So if I apply the change to the basis, I can apply the change to any vector, because the vector will be written in the new basis. So let's now discover for ourselves how the action of the map D looks like for example, for the first basis vector. So I multiply this matrix by this vector. We know the matrix is a linear map. I think it is fine if I ignore this square root of 2 for now. I think it is completely fine. Now let's try to compute this quantity. So we will get right now I'll just focus on computing the value that's inside of the bracket. I'm deliberately ignoring the square root, if you're wondering. So how does this look like? This is simply defined as the dot product of 1 with 0, 1 plus 1 with 1 and 0. So funny enough, it looks like it acts just like the identity matrix, because in the end we just get 1 and 1 again. It is not the identity matrix, I'll tell you this. So I'll tell you this now, it is not the identity matrix. you'll see why. This is a very interesting matrix. It's a very simple one as well. It's very cool. You'll see. So in the end, you could say that the action of the map on the first basis vector leaves it unchanged. It leaves it unchanged. 1, 1 just remains as 1, 1. So perhaps I'll even just completely ignore this, the square root of 2. Now let's look at what happens when we apply the map to 1 and minus 1. I think this is more interesting. See what the action on the basis vector is. Do you think it will also be 1 minus 1? So it just spits out the same vector? Or do you think it was just a coincidence? Well, let's see. This is just 1 times 0, 1 plus minus 1 times 1, 0. So it doesn't seem like it's exactly the same thing being spat out. It's minus 1 and then 1. It's kind of the opposite. So we started with 1 minus 1, it became minus 1 and 1. And here, I think the same thing also happened. Well, I don't think, I know the same thing happened. I've been trying to hint at this for some time now. The 1 got switched with the 1, but it doesn't matter because they're the same. 1 is equal to 1. But here they are not. So this 1 minus 1 gets switched up like this. Okay, then I can write now my new matrix. It will specifically consist of the vectors in the old basis, well, not the old, in the new basis, but after applying the action of the map. And we will write this as a matrix. So it is a matrix in which the columns are the actions of the map on each basis vector. I hope that is clear. And now let me show you why this is really what just happened, how it just happened. So I want you to notice that if we start with the identity matrix, so this is a bonus. First off, this is the answer. You can leave now if you would like, but let me show you now something that's really cool, I think. So your matrix D looked like this. 0, 1, 1, 0. And your identity matrix looks like this. Do you see the difference? Yes. The difference is that the rows are switched. So here the rows are completely fine. Here the rows are switched. So this is the row switching matrix in 2 dimensions. And because we had 1, 1, 1 minus 1, then we're going to flip 1 and 1. We're going to flip 1 and minus 1, so it becomes minus 1 and 1. So this action of flipping is passed on in the new basis. No matter what vector you end up writing, as 1 and minus 1 and whatever the constant might be, I just flip these two and then it works perfectly. And that's really what it is. The first time I saw this, I was very confused. But I was very amazed by it because it's very intuitive. You just take the identity matrix, you switch the rows, and so you get this. You get the switching of the rows in a vector when you multiply by this map. So I felt that this was a very meaningful thing, and I hope you agree with me, and I hope I was able to pass on some of this insight to you here in this tutorial.